told you about lithium batteries was, to be honest, only half of the truth. And I want to clarify now why the system does not work the way I just described it, or at least not in the long run. So you have to see that lithium electrodes have an intrinsic problem, and this is so-called dendrite formation. Dendrites are needle-shaped, kind of tree-like lithium structures which form on the electrode surface. This originates due to the inhomogeneous deposition of lithium plus on rough electrode surfaces during charging. So what you're doing is basically through the repeated dissolving and redeposition of lithium, you keep growing these tree-like needle-shaped structures. For this, you first of all have to know that that the battery is not always discharged up to a state that all of the lithium is gone. There's always some lithium remaining. Therefore, if it has some rough surface, it will preferably deposit at certain positions, therefore growing these dendrites. Now, this yields you, and this leaves you with a few problems. First problem is what you see here, that from this kind of needle or tree-like structure, you might lose certain parts. They might simply break off. This resembles basically a capacity loss, ultimately leading to a lower cyclability and to lower service life because you're losing active materials. The second part is that actually these dendrites are very sharp, so they can proceed to grow and penetrate the separator and therefore contact the other electrode, which basically resembles a short circuit and therefore a critical failure of the cell. And please don't have a wrong imagination about this here. You cannot simply use a very hard separator. Actually, a special feature of these dendrites is that they can penetrate even very hard materials and lead to short circuits. So even if you use very rigid, very hard materials as a separator, dendrite growth is still a major problem. There's also a very high reactivity of lithium itself with water or moisture in any other cell components. So exactly because lithium is so reactive, exactly for the reason why we chose it, it's also less suitable simply because it reacts so violently with something like water. So there's always a risk of contamination, which ultimately also leads to lower cyclability and to a shorter service life of your battery. So as a conclusion, in these kind of batteries, there's typically no lithium metal in lithium ion batteries. That's why it's called lithium ion batteries, because you do not have elemental lithium in there, only lithium ions. However, I clearly want to stress as well that there are concepts which are using lithium, elemental lithium as an anode, and this is subject of ongoing research. But there is no kind of large scale established battery system right now which really uses lithium metal as the anode simply because of the stated problems on this slide here. The grand solution to this whole problem is actually that in practice we're using these lithium intercalation or lithium insertion electrodes not only for the cathode but also for the anode. And for the anode we can use actually a very simple trick and a very cheap material, which is graphite. Graphite also comes in a layered structure, and graphite is basically simply carbon. Carbon now can also form these layers in graphite, and these layers now can, similarly to before, accommodate lithium plus between these layers. This will change our reaction a little bit as we're now using our lithium intercalation electrode not only on the cathode but also on the anode. So coming from before, where we simply reacted lithium plus electron to lithium on the charge cycle, and in the discharge we reacted lithium to lithium plus and an electron, we are now on the charge cycle reacting lithium plus C6, which is used for graphite, plus one electron to LiC6. And this LiC6 now can react to lithium plus C6, which is basically carbon again, and an electron. There's an intrinsic limitation as to how much lithium this graphite can take up, and this is exactly this composition LiC6. If we look at our electrodes now as our first component of our lithium-ion battery, we, we have stated earlier that we basically want to satisfy two major performance factors. One is we want to have a high voltage. So we want to choose materials which are from the galvanic series and which are very far apart from each other in order to obtain a high voltage. However, we will later see that this is not actually a problem from the material side. We can easily select a redox couple which has a very high potential, but we have other limiting factors in our system, which is specifically the electrolyte in this case, as we will see later. And the second part is high capacity, so maximization of the number of lithium ions which can be intercalated into the material. We've just learned that on the anode, we would like to use lithium because lithium has the most negative potential of all suitable elements, and this was this minus 3.04 volts. For other reasons, we've seen that we cannot quite use lithium in a commercial cell due to a very limited service life and because of these destructive factors due to the dendrites. That's why we are using LiC6 instead of lithium as a replacement. The great thing about LiC6 is that it actually has a similarly low standard potential than lithium. So instead of minus 3.04 volts, we're somewhere around minus 2.94 volts. And this is actually very convenient. So LiC6 kind of has the same tendency to release electrons just as elemental lithium. But we have the grand advantage that we will not create dendrite growth here. So we typically have way longer service lives if we're using LiC6 instead of elemental lithium. Now for the cathode, for the other counterpart here, there are actually a variety of different cathode materials available. One of the first commercially available materials is this lithium cobalt oxide, or also commonly abbreviated as LCO, which belongs to the class of the layered metal oxides. This is the material with which I introduced you the concept of lithium-ion batteries. Depending on your active material, you have different cell voltages for your reductive half cell, giving you an overall different cell voltage in your full lithium-ion battery. Remember, this is why I gave you a rather broad range of nominal cell voltages in the very beginning of this chapter. So now, depending on this active material, you will have a different potential versus lithium. So this is basically your cell potential, which you will ultimately have. And it gives you a different maximum usable specific capacity. So there is, relative to weight, there are different amounts of lithium which can be extracted or inserted in the corresponding structures. So the first commercial material, as I already teased you in the header, is lithium cobalt oxide, which has a potential of 3.9 volts, a usable capacity of 130 to 150 milliamp hours per gram, and it's typically abbreviated as LCO. Now, the two most modern materials in terms of high performance materials, I would say, is the so-called lithium nickel manganese cobalt oxide. Basically, it also forms these layers as we've seen before, but the cobalt can be partially replaced by manganese and partially by nickel. With this kind of strategy, we get a similarly high potential, but we can reach up to capacities of 190 milliamp hours per gram. And there is actually a variety of ratios from nickel to manganese to cobalt, all having slightly different properties. So these are typically abbreviated as NCM 111 or NCM 532, depending on the ratio of nickel to cobalt to manganese and so on. There's another typically used material which is NCA, which is the lithium nickel cobalt aluminium oxide, also reaching relatively high potentials and high specific capacities. There are two other materials which are to be noted because we avoid some environmental impact here by using iron instead of nickel and cobalt, and manganese. So we're simply using cheaply and easily available iron. However, this then leads to a lower cell potential and also typically to a lower usable capacity. So this is the so-called LFP. And the last class basically also uses very cheap manganese. So this is the lithium manganese oxide with a relatively high potential of 4.1 volts, but a very low usable capacity. So this is the so-called LMO. These electrode systems are actually carefully selected and optimized regarding the requirements for electrodes. Let's have a look now at certain requirements which are put forward towards all of these electrodes, what they have to satisfy. The first requirement we would like to have is a high specific energy density, which means we would like to have a high gravimetric energy density expressed in watt-hours per kilogram and shown in orange here, and a high volumetric energy density, which is given in watt-hours per liter. What you see now is that depending on the materials, like here we have a combination of LFP as our cathode and graphite as our anode side, which will be similar for all of these cells, and LCO, LMO, NCM, and NCA here as the cathode. We do notice that we have a clear variation in our gravimetric and volumetric energy density. Unfortunately, for LFP, which only uses iron, we notice that we have the lowest gravimetric and also the lowest volumetric energy density, which is unfortunate, but still renders it usable for certain applications where you don't mind so much about the weight or the volume of your storage. For example, stationary energy supply for home. Then we have the LCO, LMO, NCM, and NCA. And I told you that NCM and NCA are basically the high performance materials of today. NCM resembling an 8:1 ratio of nickel to cobalt and to manganese, therefore being a very nickel rich material. Now for these, you see that the volumetric energy density is actually very, very high compared to the other materials, and also that the gravimetric energy density is clearly higher than for the other systems I presented. The second part here is that you want to have a high reversibility, therefore a high cycling stability. This basically means that you want to be able to cycle your lithium from your anode to your cathode repeatedly for a very high number of cycles without losing capacity. So the easier it is to cycle the lithium back and forth without compromising your structure, the longer the service life of your energy storage, and here specifically of your battery, will be. Another factor is fast intercalation and deintercalation. So I explained to you that these lithium ions have to be incorporated and deincorporated, so intercalated and deintercalated from the structure. And depending on how fast this can happen can influence the charging speed, the rate at which you can move your lithium ions back and forth. Also, you would like to have a good ionic conductivity in your battery material because the lithium has to reach places and it has to like travel through the material to reach non-occupied positions in the material. Also, we want to have a good electric conductivity because you've seen that basically electrons have to get to all the transition metals, in our example, to all the cobalts in order to oxidize or to reduce them, or they have to travel away from the cobalt in order to resemble oxidation reaction. Also, your materials should have a very high thermal stability. So increased temperatures should not compromise the material structure or even lead to, for example, oxygen release. And the next point, what you see visualized here as well, is we want to have structural stability. One point I didn't quite note before, and one point I didn't quite visualize you before, is that actually you never fully charge or fully discharge a battery. So when cycling a battery, either actively or inactively, for example, when you discharge your phone will stop before it is fully discharged. So when you discharge a lithium-ion battery, you will always remove lithium ions from the interlayer spaces here, from the places between your sheets, but you will always leave a few of them in before you, depending on you look at the if you look on the anode or the cathode, before you fill them up again. And what this provides is basically a possibility to refill them, as if you completely empty these sheets, your layers will collapse together and it will be impossible to squeeze lithium plus ions in between them again, making these layers basically inaccessible for lithium plus, and this therefore resembles a huge loss in capacity. So your battery system or your battery management system in electrical devices will always make sure that there is some lithium left within your layers, so you can efficiently squeeze lithium plus ions back in between the layers. The next point is electrochemical stability, specifically dissolution. So if your materials are not stable at the operating conditions and at the voltages which you apply, it might happen that, for example, cobalt gets dissolved into your electrolyte, therefore destroying the material and therefore leading to loss of capacity and therefore to a shortening of service life. And the last point is so-called mechanical stability. So during this intercalation and deintercalation process, your volume of your particles will change, and also different ions have to travel into your particle, which will make it very volatile to cracking. So you want a particle which has, or material which has very high mechanical stability in order to avoid the particle from cracking apart. You see an electron microscopy picture here from such a battery particle, which is maybe 10 micrometers or 20 micrometers wide, and you see that this particle starts cracking after it's being under load and repeatedly charged and discharged. So this is something you want to avoid, because once such a portion here breaks off, you might lose this part of the material. It might be inaccessible for either electrons or for lithium ions, and each of it will render this part inaccessible and unusable to store any kind of capacity anymore. Ion batteries, at least in common setups, and these are typically organic solvents. Organic solvents with a dissolved conducting salt, which will provide lithium plus ions in order to be transported from left to right or from right to left. Now we have a key difference here from this kind of system to all the other systems what we looked at so far. Because lithium is a reducing agent, because it likes to get rid of its electrons so much, it also reduces hydrogen ions or protons to hydrogen. So this renders any aqueous electrolytes, for example, water, what we used in lead acid batteries, or sulfuric acid, it renders them unusable for this kind of system, simply because the lithium and also the LiC6 will react with this kind of solvent and generate hydrogen and basically be destroyed in this kind of process. So the electrolyte solutions must be aprotic. This means that your electrolyte should not be able to split off any kind of H plus ion. And what is typically used in lithium-ion battery systems is ethylene carbonate, which looks like this here, carbon being these gray spheres, red spheres being oxygen, and the white spheres being hydrogens, or propylene carbonate, which is abbreviated as PC. Other carbonates or mixtures are also applicable. You might say now that here are also protons, but these kind of protons here are inaccessible for lithium. This is why these kind of solvents can still be used. And the second part we're using are these conductive salts. So these conductive salts should have a good solubility in the given solvent, in these carbonates here, and they should also have electrochemical stability. So the overwhelmingly preferred conductive salt for lithium-ion batteries is typically lithium hexafluorophosphate, or LiPF6. The main message, what I want you to understand by covering electrolytes here, is that the stability of the electrolytes is, as of today, the limiting factor for higher voltages. It's not that we do not have materials which can allow us to obtain higher voltages in our cell, but simply because our electrolytes are not stable enough. You can imagine it like this. So each electrolytic system has a so-called stability window. So our electrolyte is stable from this kind of reduction potential to this kind of oxidation potential. Let's say we have a system, maybe lithium, which has an oxidation potential of around -3 volts on the anode. So you see it lies within the stability window of the electrolyte, and therefore we can consider it stable against the anode. Now we have a cathode which maybe has a reduction potential of 0.5 volts, plus 0.5 volts. Now that means our overall cell voltage is 3.5 volts. Our cathode voltage also lies within the stability window of the electrolyte, and therefore it's also stable against the voltage what our cathode provides. The issue arises if we want to further increase our cell voltage. Say we want to establish a cathode material which has a reduction potential of 1 volt. So this will lead us with a much higher cell voltage. So we are now at a cell voltage of 4 volt. But our cathode electrochemical potential will lay outside this stability window, and this means that we will continuously degrade our electrolyte, and we will not be able to statically store charges in our system, provided that certain other requirements are not setting in, like our cathode, for example, being passivated or else. So the key issue here is simply that once you leave the stability window of the electrolyte, there's the risk that you're simply not be able to store energy anymore, but you will rather simply degrade your electrolyte in the process. And somewhere they were like in a big pool of electrolyte, and there was a separator in between. This is a system which is suitable for explaining things, but this doesn't really resemble how battery cells actually look like. Battery cells are typically compact designs, and this is the reason why we need electrical separation. Take, for example, a coin cell here on the right side. You see that there are multiple components like a case, a spring, a spacer, our cathode, some electrolyte, our separator, our anode, and a gasket together with another case. It's not so important now that what are the individual components here, but notice that these parts here are all pressed together. And by pressing these together, our cathode and our anode would be in direct contact with each other. And this is due to the compactness of real-life battery systems, that basically we do require the separator for electrical separation and insulation between our cathode and our anode. The key requirement to our separator, despite electronic insulation, however, is that we have an unhindered ionic transport, so a free flow of ions because you've seen that our lithium ions have to traverse through our separator, through this membrane. Therefore, for our separators, we typically use microporous plastic foils, for example, made from polypropylene PP or polyethylene PE. A typical example of this is shown here in a scanning electron microscopy micrograph here from Selga 2325. This is a typical brand for separators. And you see that you do have this very small holes here, which basically allow ions to pass through, but the whole bulk separator still provides electrical insulation. The thickness of such separator is typically 20 to 30 micrometers, and it has to fulfill various other requirements, such as chemical resistance. It should be low in manufacturing cost. It should be very much light, so we do not want to have additional weight in our cell. It should be temperature resistant to prevent a shutout or shrinking. What is shutout or shrinking? Well, basically these kind of separators are made out of polypropylene and polyethylene, as I just said. So when your cell temperature rises, typically to around 130, 140 degrees C, they will kind of become soft. And through the pressure in the cell, you might close these pores here. And therefore, ionic transport might not be possible from one side or another. If you raise the temperatures even further, the separator will simply degrade and shrink, and therefore allow for cathode and anode to contact, therefore create a short circuit and a critical failure of your cell. So this is something which the separator necessarily has to provide to the cell. Regarding the other factors, the separator will always provide kind of a trade-off. You have to see that a thinner separator is preferable regarding energy density. This is because the separator does not provide any capacity. So it's simply basically dead material in your battery, which does not provide any additional service life or any additional capacity to your application. So you want to make it as thin as possible. However, you also would like to have a relatively thick separator because you want to prevent piercing or short circuits, for example, through a mechanical impact or simply through aging over time. And this is, of course, something which has to be weighed very carefully so your separator doesn't get too thin, which will raise the risk of, for example, fire in the battery and therefore critical failure. There's a lot of innovation going on in this field. For example, coating these kind of separators with ceramics to provide higher temperature stability and also avoid having this shutout or shrinkage effect.